Today we will start chapter number 34 and our topic is magnetic force acting on a charged particle. Here in this figure you can see that there are actually three figures. You can see the parallel lines in all these three figures, and then there is a charge q in all these three figures. So the parallel lines are indicating the direction of the magnetic field, which in all the three figures, as you can see, is directed towards the right, and it is almost a uniform magnetic field. And the other thing which you can see and which is common in all these three figures is the charge q. But here in figure number 1, the charge q in this figure number 1, the charge q is having zero velocity. In figure number 2, the charge q is moving with some velocity which is parallel to the magnetic field B. And then in figure number 3, the charge q is moving with a velocity which is perpendicular to the direction of the magnetic field. So we are to determine the magnetic force acting on this charged particle in all these three cases. Now if you are able to answer the question at this stage, it means you have a pretty good background about the magnetic force acting on a charged particle. But if you are unable to answer this question, then let us first go through the lecture, and then we will come back to this page and we'll try to answer this question. Another thing which we must keep in mind before deriving the equation for this magnetic force acting on a charged particle, we must bear in mind that whenever we are talking about the magnetic field, we will talk about B. This is the letter which indicates the magnitude and direction of the magnetic field, just as E was used to indicate the magnitude and direction of the electric field. So to derive the equation for the force on a charged particle in a magnetic field, let us first do some experiments, and for that purpose we will project q with different situations in a magnetic field. In the first case, we will project our charge q in the magnetic field B parallel to the magnetic field. That is, if this is the velocity, if the upper arrow shows the velocity of the charged particle and the lower arrow shows the direction of the magnetic field, which is denoted by the letter V, if both are parallel, and it means that the angle between the two will be equal to 0. The angle between V and B is equal to 0. Then what will we observe? That the magnetic force acting on such a charged particle which has a velocity v parallel to the magnetic field, the magnetic force acting on such a charge will be equal to 0. But if we project a charge q in a magnetic field perpendicular to the magnetic field, having a velocity v which is perpendicular to the magnetic field, that is, we are projecting a charge q with a velocity v perpendicular to the magnetic field. This is the direction of motion of the charge q, and this is the direction of the applied electric field. So in such a situation, when angle is 90°, when angle between v and b is 90°, the force acting on the charge particle will be maximum. This is our first observation. That is, in the first observation, we project the charge q into the magnetic field at different angles. So here we are keeping b constant, we are keeping the magnitude of the charge constant, we are keeping the velocity constant, but the only thing which we are changing is the angle between the magnetic field B and the charge particle and the velocity of the charge particle. So we will project it at different angles in this magnetic field at different theta. Here you can see B and V are making different angles. So the result which we will obtain is that for theta equal to 0, the force is 0. The magnetic force acting on the charge particle is 0. And for theta equal to 90, the magnetic force acting on the charge particle is maximum. And for angles in between 0 and 90, the force will vary accordingly. The smaller the theta, the smaller the force. The greater the theta, the greater will be the force. This is our first observation. Now for our second observation, we will increase the velocity with which the charge is projected in the magnetic field. So for each case, we will increase the velocity. We will keep on increasing the velocity of the charge particle and will project it into the magnetic field with different velocities, and we will see that each time we increase the velocity, the force acting on the magnetic field will also keep on increasing. So in this case, we will keep theta constant. We will keep the magnitude of the magnetic field constant. The only thing which we are changing is the velocity of the charge particle entering the magnetic field. So in this case, the observation which we get, or the result which we get, is this thing, which is that the magnetic force acting on the charge particle increases linearly with the velocity. For greater velocity, the force is maximum, the force is larger, and for smaller velocity, the force is accordingly smaller. The next observation is obtained when we change the magnitude of charge. That is, when we allow the charges of different magnitude to enter into a magnetic field having a fixed value of B with the same velocity and at the same angle. We project Q of different values, means of different magnitudes, into the same magnetic field and with the same velocity and with the same angle theta. So this will give us the relationship between the magnitude of Q and the magnetic force B acting on that charge. And the observation, the third observation which we obtain is that the force, the magnetic force acting on the charge is directly proportional to the magnitude of charge. So next observation is obtained by changing the